Hey, welcome back to Fat Mama Physics. This is the third video on friction force, the last but not least. And a little bit heads up, it's going to get rough from here because we are going to deal with 2D forces. And the solutions are going to get much longer, as well as I'm going to be solving everything through substitution and plugging in numbers the last step, which is what I prefer over plugging in numbers throughout the way, which gets really messy. Again, I'm going to do the first problem and you will do the second problem down below. So without further ado, hopefully keeping this video as short as we can, that's going to be tough, and let's get started. In 2013, there was a winning mule poll of 5,000 kilograms. So I'm assuming this big crate here is 5,000 kilograms. The ropes that are tied to the 5,000 kilogram wooden crate make a 17-degree angle with the ground. So that's it there. The coefficient of kinetic friction between the wooden crate and the dirt is 0.29. That's mu k. If the mules are pulling with a force of 15,300 newton, that's our applied force, what is the acceleration of the wooden crate? Ooh, ouch. Okay, so first and foremost, let's first start with a free body diagram. So here we have the basic drawing here with force due to gravity, normal force, force of friction. Fa is at an angle. Now, if we want to solve this properly, we can't use the full-blown Fa because it's applied in a diagonal, meaning it has force components that we have to deal with. So let's break them down first. We have the applied force, part of the components is along the x-axis, which I will label right now, and part of that force is along the y direction, which is in the vertical direction. I'm going to label the forward direction being positive and the upwards direction being positive for both axes. I think it's going to help us if we actually write down what our Fax and Fay are based off of what Fa is in our right triangle. At this point, I expect you to know your trig very well, so you can write down this equation without needing to go through the many steps of trig. But quickly here, along the x direction, this is adjacent to the 70-degree angle. So if we want to figure out Fax, this is our hypotenuse, Fa, multiplied by the cosine of 17 because we're interested in the adjacent side. Vice versa, for Fay, this is our hypotenuse multiplied by the opposite side. This is the opposite side of 17 degrees, so that's sine of 17 degrees. And this is these two we will use and need in our follow-up equations. Because we have forces in the x and y direction, we are going to separate our Fnet equation amongst the two. First, we are going to deal with the x direction first, seeing what we need to solve for the acceleration of our wooden crate. So Fnet x here is equal to max. Along the x direction, we have our forward force that we are interested in, which is Fax, which is opposed by our friction force, FFk, kinetic friction, and that's equal to our mass times acceleration along the x direction. We are going to solve for the acceleration by dividing both sides by our mass. We get the acceleration equals to Fax minus FFk over m, and which one we can substitute we can substitute Fax in already, which gives us Fa cosine 17 minus FFk over m. We now need FFk, the force of kinetic friction, to move on. We do know that the force of friction, kinetic friction, is equal to mu k Fn, okay? In which we need to know Fn first. But let's put this mu Fn in here first, which then tells us we need to know Fn first before we can move on. And to find out Fn, we need to examine the vertical forces. So then we are going to, on this side, talk about the vertical forces along the y-axis, in which the acceleration is 0, which means F net in the y direction is also 0. If that's the case, then the opposing forces must balance. So the upward forces will equal to the downward forces. Now, the upward forces, yes, there is Fn, but notice there is also the upwards component from our Fa, which is Fay. This is equal to our downward forces, which is only Fg. Let's solve for Fn first by moving Fay to the other side. We get Fn equals to Fg minus Fay. We already know Fay is here, Fa sine 17, that we can use to substitute in already. We also know that Fg is mass times gravity, and that is something we can use here as well instead of Fg. Now we have the complete picture of Fn, which then we can substitute back over to the other side along our x direction F net equation over here. So let's do a substitution. We get Fa cosine 17 minus mu k, and all in brackets. Don't forget to bracket this nicely. Mg minus Fa sine 17, and all of that divided by the mass at the bottom here. So what I'm going to do is I am going to distribute this mu k into each of these terms in here to maybe help us see the full picture. Notice now that we have minus mu k, and that minus is going to multiply by another minus. So when we multiply this in, these two minus signs multiply to give us a positive sign. So we get positive mu k Fa sine 17. And all of that divides by mass. Phew, this is the final step where we get to substitute in all our numbers to calculate for the acceleration of the wooden crate. We have the applied force, which is 15300, cosine 17, minus mu k, which is 0.29. The mass of the crate is 5,000 kilos. Oh, and right, gravity, we know that, 9.81 meters per second squared. I'm running out of space, so I'm not writing in units. Sorry about that. Plus mu k again, which is 0.29, times the applied force again, as well as sine 17. All of that divided by the mass, which is 5,000 kilograms. Phew, all right, let's put that all in our calculator. Okay, so after double checking my answers by recalculating, I get 0.3408. I'm going to round this up to two significant figures, which is going to be 0.34. And that's 0.34 meters per second in the positive direction forward. Phew! Aside from all that mathematics and everything, there's a few key things that I want you to take away from this problem. Number one, when we're dealing with forces in a diagonal involving 2D forces, don't forget to break down your components into your x and y. The second thing that I want you to take away from this video is the fact that we need to separate your forces in the x and y, vertical and horizontal forces, when we're dealing with F net equations. So notice that my vertical forces don't belong in my horizontal x F net equation over here. We separate the vertical and horizontal forces. The other key thing I want you to notice is the fact that your Fn here is not equal to your Fg. More or less, if you take a look at this carefully, this is mg minus FAS sine 17. So this is less than the force due to gravity. if you think about it, when you're pulling something across the floor, wouldn't it be easier to pull it in an upwards direction so you're decreasing the impact of your object against the ground, decreasing the force of friction here. And the reason why that's happening is because this helps you reduce the normal force on the ground, the contact between the object and the ground. So this is why mg, you have to subtract this applied force in the vertical direction from the force due to gravity, because this upward force helps eases off that pressure on the ground. So normal force is less than it was before. On the contrary, think about if you were, say, pushing this box in the forward direction, but in the downwards direction. Would it be easier to do this, or would it be easier to pull it up instead? So these are the things you want to think about involving the normal force, because now we're dealing with 2D forces in which the normal force can increase or decrease depending on the other vertical forces acting on this object. Here I have a summary of the key things I want you to grab out of this question. So moving on to your turn. Oh my god, it sounds scary. Give it a try. You can do it. I'm going to help you a bit here. Okay, first off, here's the question. If the coefficient of static friction between the wooden crate and the dirt in the previous question is 0.5, so that's mu s, static friction, what pulling force do the mules need to get the wooden crate to start moving? So you need an FA, but this time you want to get the crate to start moving, assuming the crate is not moving to begin with. So you have to bypass the static friction, which is mu s Fn. Hint from the last problem, Fn is not going to be Fg, okay, because your FA is still going to be applied at a 17-degree angle on a wooden crate that is still 5,000 kilos. Before you dive into this problem, I just want to remind you something, mathematical tactics that maybe you've learned in math or maybe you haven't. First is the distributive property versus the factoring. So they are opposites. What does that mean? Distributive property was what we did in the last problem, where I distributed something into brackets. So for example, let's say I have 20 apples plus 10 apples inside these brackets. I'm going to multiply the whole thing by a juicy factor. So the juicy factor applies to these guys and to these guys. In the end, I'm going to end up with 20 juicy apples plus 10 juicy apples, and yes, that's 30 juicy apples, okay, very juicy, versus factoring. On the other hand, if I have 20 juicy apples and 10 juicy apples, I can factor out a juiciness factor outside of my brackets. Well, I have to put in brackets first, and then that's going to give me my juiciness outside of these brackets, and 20 apples and 10 apples on the inside of that. So that is something that you can do if you have one common factor between the two terms inside of a set of brackets. Okay, so hopefully that might give you some bit of a help when dealing with this problem here. Otherwise, feel free to watch my solutions on Fast Play. Good time to pause, and here I go with the solutions. Let's first start off with a free body diagram of the wooden crate. You have Fg and normal force acting in opposite directions, force of static friction in the backwards, and Fa at a 17-degree angle, in which we need to separate these into the y and the x component. So here's the positive direction in the forward and back in the upwards direction along the y and x axes. As for the Fax as Fa cosine 17, Fay Fa sine 17, just like the previous problem. So first, let's start off with the x direction, in which the Fax, the horizontal component of the force, must be greater than static friction in order for the box to crate to start moving. So that's Fa cosine 17, by the way. Now we are going to substitute the mu s Fn into the force of static friction, meaning we need to know Fn, and to do that, let's look at the y direction where acceleration is 0, F net is 0, meaning that the upward forces must equal the downward forces. The upward forces include the normal force and the vertical component of the applied force equal to the force due to gravity. The applied force in the vertical direction is Fa sine 17, and the Fg is just mg. So putting that in and solving for Fn, we get the following, in which we need to substitute onto the other side of the equation, on the other side of the page over there. So putting everything in, where Fn is mg minus Fa sine 17 in purple, we will need to distribute mu s into both those terms, giving us the following. Notice we have Fa in two of the terms, and to solve for Fa, we need to combine the terms first. So that means putting them on the same side of the equation. So doing that first, putting them together, we get both the Fa's together, and then the next step is to factor them out from the two terms. So putting brackets between those two terms first, then factoring Fa outside of the brackets, we get now Fa, and in brackets cosine 17 plus mu s sine 17 inside the brackets. To solve for Fa, we can now divide what's inside the brackets onto the other side of the equation. So then Fa, we get the following. Mu s is our coefficient of static friction, which we know is 0.5, and mass is 5,000 kilograms, and gravity 9.81. Substituting everything inside in this equation, we get the following. And then putting this in your calculator, don't forget all the brackets, making sure you do every step very carefully, we get 22,245 newtons, which is the minimum Fa force. So Fa needs to be greater than that. If we round up to 2 sig figs, it must be 23,000 newtons. Okay, so these are the solutions. Now for this tool, so just a quick recap. In order for you to solve this, you need to make sure you find an Fa in which the Fa x component is going to be equal or larger than the force due to static friction. So to overcome that, we need to equate the two over here. And we did the same thing that we did before by solving for the normal force, substituting that one in. It got a little tricky when you had to solve for the applied force Fa when there were two of them in the same equation in two separate terms. So that's when I talked about the factoring and the distributive property comes into play. So you needed to factor the Fa out of when the two terms are side by side. In order to get them side by side, you need to put the Fa's both on the same side of the equation. So then when you put the brackets in, you can then factor the Fa out of the equation, and in which when you have Fa times something in brackets, you can then divide both sides of the equations by whatever is beside the Fa to isolate for the Fa. We got an Fa value of 22,245 newtons to move the crate, and so this time when you do the rounding, it would be better to round up for 2 sig figs, because you need at least this much force. Anything less than that is not going to get the crate to move. So that's why I rounded up to 23,000 newtons of applied force to make sure you get it moving. Okay, so those are the solutions. I congratulate you for getting through this video. You've done a fantastic job. If you've patiently gone through the whole thing, if you've given it a try, great. You're doing the best that you can. If you were able to solve most, if not the whole thing, man, you should be proud of yourself. Okay, good for you. Hopefully you learned something from this video, even if it's something basic, to help you with your problem solving in the future. Thank you for watching this video. Keep it up. Fat Mama Physics salutes to you, and signing out.